Everyone can hear me? In your way. Cool. Pretty much 11, so get started. And hopefully you are in the right room here to learn about profiling PHP applications. Before we get started, just a little bit about me. I'm Michael. I'll be around for the rest of the day. Can you say hello? I'm Heap on Twitter. And I work at a company called Data Sift, just outside of London in the UK. What I'm going to be talking about is something that I learned there in my day job. It's not a contract example. This is something that I've had to do day to day.
I'm sitting at the front, completely on the left.
Quick disclaimer, these benchmarks were taken on VM. They are representative, but not 100% accurate. We did run this code on bare metal machines introduction. We saw similar gains. But when you see the numbers, just remember that they have come off a virtual machine, a virtual machine. So, we're going to learn about profiling PHP. That means we're not going to cover front-end optimizations, we're not going to talk about networks, we're not going to talk about databases. Like, those are entire talks in their own right. We will cover quick wins. We'll cover naive profiling. We'll take a look at 8H prof and 8H doing. And then a couple of other considerations that you could have when profiling. So, we start with the quick wins. How many of you know about PHP's go faster mode? This is a real thing. You might know it by another name though. Maybe apt-get upgrade PHP, or young upgrade PHP, or for those of you like myself that use Dodge, Hackman, best package manager in the world. PHP 7 is fast. It's twice as fast as 5.6 for WordPress for Magento. It's 1.5 times faster for Drupal 8. Before you even start digging into your code and profiling, just upgrade and you get all of these performance benefits for free. Think about the work that you're doing. Does it need to be done right now? Generating emails to send to customers. When they click a button, do they have to sit and wait for you to send the email? Can that be pushed off into an asynchronous job using Gearman, using Beanstalk-D, RabbitMQ? Think about the code that you're writing and whether it needs to happen right now, because the code that doesn't run is the fastest code of all. Now, I'll just set the scene a little bit, explain the code that I had to write, what problem I was trying to solve. And as I mentioned, this is a real-world example. It's not contrived. We were inserting into a database, and as you know, databases don't like it when you try and insert keys that don't exist. The one in question was Google BigQuery, and the way the data platform works is, at the end of it, you get a piece of JSON, and there can be any number of keys in there. So we didn't know in advance what we could insert into the database. And to make it more fun, Google BigQuery is entirely asynchronous. So when you push data to it, it doesn't tell you if it's accepting it or not. It just kind of fails at some point in the future. So what I needed to do was pull down the scheme from BigQuery, iterate over all of the keys in my data, and run the diff. So this is a simplified version, but given this piece of JSON, I needed to generate these keys. So interaction.content and interaction.author.name. And the algorithm that I use to do that is I start at the top, and I step in, and I say interaction. Is the value a scalar value? No, it's not. Okay, let's step in again. Is it a scalar value this time? Great, it is. That means that interaction.content is one of my possible keys. And then we start again. We go back to interaction and say, author, is it a scalar value? No, step in. Name, is it a scalar value? Yes, it is. And so on and so forth. So, It's not a particularly complicated algorithm, but it was one that actually ended up being quite slow. When I started writing this algorithm, the first thing I needed to do was get some test data. So I ran a stream, I downloaded a couple of 100,000 pieces of data, and I needed to get them into my test harness. So I wrote a little bit of code that looked like this. We read contents from the file. Because it's new line delimited JSON, we had to explode on new line and decode each line individually. And I thought, I wonder how long this is taking, so I'll just stick micro time before and after and work out the difference. It's pretty naive, but it gives me a decent indication of how this is performing. I was testing this with 50,000 items, and it took about 5.7 seconds on average just to load the data. I wasn't even applying the algorithm yet. 5.7 seconds, and I thought, it's not bad, it's not great. I wonder how we can improve it. So I went back to my code, and I had a look, and I thought, reading off disk, pretty standard. But actually, JSON decode, because we're doing it on every line, we're actually calling this 50,000 times. Do I need to call it 50,000 times? I call it once. So I did a little bit more code, and I said, if this cache file exists, just read that, call it in one. And if it doesn't, we do it line by line, but afterwards we write a cache file where we just get the array, we JSON encode it, and we stick it in the cache file. At this point, the first run will be a little bit slower, and every run after that we use the cache, and it will just be one JSON decode. So I ran that. Without the cache, it took 11.7 seconds, and with the cache, it took 8.7. The cache was quicker, makes sense to everyone. Like, I'm not being stupid, like, the cache file should be faster, right? I was happy. But, really, I was just guessing. I didn't know if JSON decode was faster or slower. The numbers supported it, but those of you that are paying attention, 11.7 seconds. Why is it taking 11.7? The average before was 5.7. Like, what's changed there? So I decided to dig in. Let's do it properly. The naive approach kind of works, but it wasn't really supporting the data that I saw earlier. Even though it was supporting my hypotheses, I wanted to get some more detailed information. So I went and I installed XHprof. For those of you that have never used it, fantastic tool, open sourced by Facebook a couple of years ago, and it's built as a PHP extension, so you need to install it with Peckle, add it to your php.init, and it actually comes with a load of library files, which I'll cover a little bit later. Once you've got it installed, it's really simple to use. At the beginning of your script, you run xhprof enable. And here I'm saying I want to profile CPU usage, and I want to profile memory usage. Then you get your code, it does its thing, and at the end, you run xhprof disable. And that returns an array of all the data that it's collected so far. That array, it looks a little bit like this. This is one data point. There is 10, 20, 30, 50,000 of these in a single run. But I've pulled out the one for JSON decode. This is without the cache file. As we can see, it ran 50,001 times. That confused me, but then I realised it was a new line at the end of the file, which means it tried to decode an empty line afterwards. Something that I'd missed. XHprof wrote it straight out. We spent 4 million? Yeah. 4.3 million microseconds, 4.3 seconds of wall time inputting data, 4.7 seconds of CPU time. Our memory usage was 800 megabytes. This is just XHROF, it gives it to you straight away. But this isn't that useful. Like I said, this is 1 of 10, 20, 50,000 items. Fortunately, XHROF comes with a UI as well, which helps you to summarize this. Those library files that I mentioned earlier, if you include those, it exposes this XHROF runs defaults class that you can use to save runs to disk. And when I say save runs to disk, I mean it serializes the array and writes into a file. It's nothing clever. But then it's available for use in other applications. Things like the XHROF UI. Now, the UI is not that pretty. And it works. This is the overall summary for the import without the cache. This run, 12.6 seconds. I actually don't like the image so much. This works. There we are. After the text, everything lines up nicely. 12.6 seconds to run. 900 megs of memory usage. This is without the cache. And with the cache, it took 9.5 seconds. So actually, XHROF is saying, without the cache, it's taking longer than with the cache. But I'm still not convinced. This is a summary. It's telling me what micro time showed. It is taking longer overall. But where is that time actually going? Is it going into JSON decode? Is it going into file get contents? XHROF can tell us that as well. This is the code graph. It shows what functions ran, how many times, how much memory usage, how much wall time. And you might notice down here in the bottom right, JSON encode and file put contents. This is the code that actually writes our cache file. 5.2 seconds, 40% of our entire execution time. This is why our non-cached version is slower. I'd forgotten that was actually writing the cache file out as well. Something very easy to miss, but XHROF surfaced it straight away. I hadn't even thought to account for the writing of the cache file. If we take a look at the actual file get contents and decode time, is what? 46% of the time, 5.9 seconds. Remember, our cached version was 8. So actually, our non-cached version is looking faster again. To prove it, I commented out the line that load the cache, profiled it with XHROF, then named the cache, profiled it again. And these are the values that I came out with. Without the cache, JSON decode took 4.3 seconds. That's running JSON decode 50,000 times, compared to running it once with a much larger input string, which took 6.2 seconds. It turns out that JSON decode doesn't like large strings. It's much happier doing lots of small iterations than one large string. I didn't know that, but now I do. So I got a little bit sidetracked, went off on a little bit of a tangent, but it meant that I had XHROF installed already. It was useful for profiling the rest of my algorithm development. So back to the original task. If you remember, we have JSON that looks like this. We want to generate a list that looks like this. When I was testing the data loading, I was working with 50,000 interactions. My little VM didn't like running the algorithm over 50,000 interactions, so the numbers that you're going to see now are based on an input set of 1,000 items. started by writing some tests to make sure that my algorithm was actually working accurately, and then just jumped straight into it. Went for version 1. It looked something like this. Splashing at the top, we want to run for every field in the interaction. If it's an array, or if it's an object, it's not scalar value, so let's recurse down. Otherwise, let's take all of the keys that we've seen so far, join them with a dot, and put them into a list for reading later. Because this runs on a single interaction, and I had 1,000, I also needed some kind of aggregation function. So I wrote this generate all function, and it just says, for each interaction, run the generate function, and merge it back into the original list. And then eventually, we don't want falsy values, so we use array filter, and we want to know what the unique values in there were, so we use array unique. This code passed my tests. I was happy enough with it, so I thought, let's see how it performs. Let's run it through xhprof. And it took about 8 seconds. Again, not too bad, and not too great. Considering this is 1,000 items, not 50,000 items. It used 19 megabytes of RAM, and its peak memory usage across the entire execution was 37 megabytes, with a grand total of 355,000 function calls. For this code, 355,000 functions. So, taking a look at this code, does anyone have any ideas where our time's going to be spent? The recursive call? Anyone else? Array merge? Any more? Okay, let's take a look at the call graph. It's a little bit bigger this time, but as you can see, there is a huge red box. So array merge. 40% of our time was spent in array merge. Not even doing anything that we wanted to, none of our business logic, just merging arrays. 40% of the time, that's what, 3 seconds, 3.5 seconds out of 8. Seems like a good place to start to me. So I went for version 2. And all I wanted to do was get rid of array merge. So I went into my code, found where array merge was called, and I changed it to a for each. I couldn't believe this would work. Loops are slower than function calls. That's just common knowledge. But xhprof told me that array merge was slow. I figured if I try this with xhprof again, it will tell me if this was faster or slower. The beauty of profiling, you're not guessing anymore. It's going to tell you exactly what's happening. So I changed it here, and I changed it in the generate all function as well. So called array merge, and we just changed it into a for each. So we were at what, 8 seconds before? Maybe we can get down to 5 seconds. That saves us about 40% of the time. 3.6 seconds. Just by removing array merge and going for each loop. I was amazed. I did a little bit of reading, dug into PHP source code to see how array merge actually works. Because I couldn't believe that this was actually performance optimization using loop rather than array merge. And it turns out that array merge is, the way it works, is it creates a new array, and then it iterates over everything in the first array and adds it to it, and then it iterates over everything in the second array and adds to it. So then you've got 3 arrays, 1 containing all of it, and 2 containing half each. If the first array that you pass to array merge is large, and the second one is small, you'll get huge performance gains by just appending the second one to the first array. Because if the first one is 10,000 items and the second one is 100, that's actually only 100 copies. Whereas if you use array merge, that's 10,100. So this is a 55% saving, 55% time decrease. And this is only with 412 unique keys in our data set. In production, we could have had 10 times that. So I'd say this is a pretty good saving so far. But I'm sure we can do better. So let's go back to XH graph. Let's go back to the core graph. See where the big red boxes are this time. Got this at the top. So target is my class. Target is my namespace. V2 is the class. And the method is called generate. And what XHproc will do is it will split it out by recursion level as well. So we've got the top level, recursion depth of 1, at 2, at 3, at 4, at 5. And it makes sense. As the recursion level gets deeper, the boxes get smaller. Now, having big red boxes being your code isn't a bad thing, because it means that your program is actually spending its time performing business logic, which is what we want. So I started to look elsewhere. I thought, I'm happy with it doing the checks, generating the keys, but what else can we do? And my eyes got drawn down to this bit here, this implode, which is 6.3% of all time. But when I was down there, I noticed that some of the other boxes, although they're not yellow, had bigger numbers. Is numeric, is array, is object. Is array and is object account for 7, 11, 12%. 12% of our entire runtime. And that's just to check if we need to recurse, or if we just need to generate a key at that point and add it to our list. So I thought, is there any way that we can combine those? Is there a function that will check if it's an array or it's an object? So I went for version 2.5. Quick change. Instead of checking if V is an array, if it's an object, I decided to check if it's an instance of traversable, which is an interface. 300 milliseconds. Right. It's incredible. We took 8 seconds. Now we're down to 274 milliseconds. That will be too good to be true. And it was. I ran my tests, they all failed. It turns out that arrays and objects don't implement traversable. So it was being shortcutted, and it was actually only generating the top level of keys. When you're refactoring, which is what profiling is, you're making changes, you need to have confidence in your changes. That's why I started by writing the tests. I wanted to make sure that the code I was writing would solve the problem that I had. But it also helped catch this. I mean, it took me a minute or two to click and think, actually, is this actually doing what I think it is? Because this just feels too good to be true. So I went back to the drawing board. Went for version 3. Still focused on is array, is object. So how can I optimize this? What am I actually trying to work out here? And I thought back to how I defined the initial algorithm. If it's an array, if it's an object, recurse. If it's a scalar value, add it to the list. I inverted that. If it's not a scalar value, recurse in. That's now one check instead of two. I could save us 7% of execution time. 2.9 seconds. Down from 3.6, just by combining those checks. 3.6 seconds, then to 2.9. Now this is where I left it. This is where we shipped it to production. We started at 8 seconds, now we've under 3. It was good enough, I'd spent enough time on this. Let's ship it, let's get the improvements. But for this talk, I'd said I'd keep going. I wanted to see just how fast I could make this code. So we've got version 4. Version 4. Anyone want to guess how fast this code can possibly be for 1,000 items? Bearing in mind we got down to 2.9 seconds from 8 initially. 100 milliseconds. I wish PHP was that fast. Started at 8 by applying what? An array merge refactor, a scale-on refactor, and one or two other things. I actually managed to get this down to 1.2 seconds. Not bad for a couple of hours' work. Now we've flown through this today. It's taken us 15-20 minutes to get from version 1 to version 4. But I knew what refactorings to apply. I've done this before. I've used XHprof. When I first did this, that couple of hours was learning how to install XHprof, learning how to read the values in there, working out what to change. And then after that, you just have to get over that initial hurdle, get it installed, play with it, see how it works. So, 1.2 seconds. When I looked at the code graph, it showed me that I had actually missed an array merge. So I changed that. It's not quite as nice to read, but still fairly reasonable. But then we started to get into some of the less pleasant hacks. Things like get type. Get type is a lot faster than is array, is object, is scalar. So what I did was I used get type and got the first letter, and if it was an A for array or for object, it saved a lot of time. I mean, everyone would have told me what that did though. I'm pretty sure if I wrote that in my code workers would have rejected it once they reviewed it. They would have said, what is this code doing? There's a fine line. It's got to be performant, but it's got to be readable. So otherwise, the next time you come back to it, you wrote it, come back to it in 6 weeks, 2 months, you've got, what does this code do? And then it'll take you an hour to work it out. And that's time that you've lost. For the trade-offs, make sure that you know where to draw the line. My speaker notes have got the word calligraphy. I almost said that out loud. So far we've just looked at the code graph, not calligraphy. But XHprof has quite a good UI. I say quite good. It's horrible, but it's kind of like Stockholm Syndrome, where you work with it enough you start to enjoy it. And it looks like this. It's really powerful. You can sort by inclusive and exclusive wall time. Inclusive is all of the time it took for this function to run, including all the functions that it calls. And exclusive is how much time it took for this function to run, excluding all child calls. Generally, you want to work with exclusive because you just want to work to optimize that one function. We've got the same for CPU time, for memory usage. For memory usage in particular, we want to be working with exclusive because otherwise you're getting all of the child calls memory usage as well. You don't know how much your functions are actually using. This is good. but most of this information is available on the call graph, and I just like the big red boxes. I don't have to look, my head just goes straight to it. It does have a couple of other useful bits though. Things like, I can click into any of these functions, and it will show me this, which is the call stack. I can see that array merge is called in two different parent functions, generate all and generate at the first level of recursion. And I can click into those and see the parent functions of those and click again. XHProf only manages one level of parent function calls, but because every function has a parent, you just keep clicking and clicking and clicking until you get to the top. It also has a comparison view. This is version 1 versus version 4. Version 1 had 355,000 function calls. Version 4 had 93,000. So that's a saving of 73.8%. Seeing numbers like this is really nice. You know that your summary time has gone down, but when you're trying to justify the work that you've done, being able to say, hey boss, look, I saved 86.8% of our wall time. This runs 86.8% faster. And I mentioned trade-offs before about code readability. There are also time and space trade-offs. For example, my version 4 ran 86% faster, but it actually used 2% more memory. It's not big, but it's worth considering. If you're limited by memory and not time, then maybe you'd optimize in a different way. You have to know your constraints. This comparison view, when you open it, it also has a little code graph link. And you'll see it like this. Again, version 1 versus version 4. Version 4 has 0 milliseconds of array merge. I killed them all. That's a saving of 3.4 seconds, just in array merge. So you can see how each function call has been optimized, as well as the overall runtime. Now, I said that I quite like this UI. There are nicer ones available, the most notable of which is XHGUI by Mark Story and Paul Lenheimer. It takes exactly the same data. It uses XHProf enable and disable, but it stores that data in a database rather than serialize PHP files on disk. It draws nice little graphs. This one here, this is array merge. I hovered over this, it told me that that's my call to is numeric. And that took 329 milliseconds. It also has a list of all the functions underneath with the number of microseconds that each one took. It has call graphs as well, just like XHGUI. They look a little bit nicer. You can mouse over, see things like call counts. It's a little bit more interactive, but it's still the same data. It's just another UI on top of the XHP data. It's got this run history. When I go to XHGUI to the home page, it shows me all of the profile runs that I've made. It shows me the wall time, the CPU time, the memory usage. I can click into each URL. This is actually a command line script, so it's just taking the file name. But I can click into each, and I can see all runs for that file, for that URL, so I can compare all the time. Or I can click on the time, and it will show me data just for that run. I've just remembered another feature with XHProf, the UI, not this one, the other one, that I forgot. When you're viewing a run, what you can do is take the run ID and make a comma separated list in the URL, and it will take the average of all of them. So you can run it over the course of a day, a week, a month, different times of day. and have XHProf show you the average, which is really useful for normalizing outliers. I can't believe I forgot that. It's really, really useful. So, XHGUI has this run list of historical runs. You can click in, see the runs for each version, see a specific run. It also has a diff view, show you the number of function calls inclusive wall time. This is all data that we've seen before, just in a slightly nicer UI. And it's database backed, so instead of just writing to disk, you can run XHProf on multiple different environments, give them different identifiers. So I've got version 4, version 3, have staging, integration, developer, and you can build that up all the time, have one central database, have lots of different clients connected to it. That's not possible with XHProf. There's a fairly new kid on the block, probably been a year or two now, a year, 18 months, called Blackfire. This is by Essential Launch guys. I am working with FOSDEM, so big disclaimer, this is not free. They've given me an account to play around as part of the champion program, and actually, I'm really enjoying working with it. After years of XHProf, it's quite nice. I mean, it's got all the same things. Inclusive and exclusive, function calls. This is the same code that I ran before, just in a slightly different layout. It's got code graphs. Although this does have something that XHProf doesn't. And that's compilation time. And the initialization time of the engine. It tells you how long your PHP file took to compile. So next time your coworker comes along and says, I know how to make the code faster. You say, right, what is it? What's this great idea? And they say, we've read something about the PHP engine, and we're going to go through and we're going to change all of our double quotes to single quotes because it can voice it faster. You can show them 0.01% of the time it was actually voicing the file. Actually zoomed in so you can see it. It shows all kinds of things. It shows wall time, disk I/O, CPU usage, but it also shows things like network usage. How many calls out to the internet did it make to a local network? What was the data transferred? The disk I/O in particular is interesting for me because if you're doing a lot of reading and writing from disk, that's probably a bottleneck. Disks are slow. And of course it has a run history like XHGUI. On this run history, it's got these compare buttons. You can choose any two, say from this to this. And it shows you these boys. Similar information, just a slightly different UI. Array merge went from 3 seconds to 0 seconds. Perfect. The boy goes this way, to the right, if you go worse, this way, if you go better. There are lots of other tools out there. The classic is Xdebug with cache grind, with kcache grind or web grind, which is a web UI for cache grind files. That will show you function calls, CPU time, things like that. But I would say that the UI is actually worse than XHProf. There's Typeways, which used to be Quafu Labs. There's New Relic. There's Cache.io, which I learned about yesterday at PHP Benelux. It's quite interesting. And I want to give a special mention to PHP Bench by Dan Leach. And the reason I like PHP Bench is it doesn't tell you where your code is going. It doesn't say array merge is really slow. It just runs code. And it says it took this long, we'll do this many iterations, we'll work out the standard deviation. And the reason I like PHP Bench for this is it helps get rid of what's called the observer effect. And we've all heard a watch kettle never boils. That might be more common in England. But if you sit a watch kettle, it will never boil. Leave it alone, and it'll be fine. Programs are the same. If you're instrumenting them with XH cloth, okay, XH cloth is pretty clever. It knows how much time is spent in each function call, and it knows how to account for itself. But it's still doing something. PHP Bench just runs your code. It watches from the outside. It actually just uses micro time. But over a number of iterations, you can work out a general trend. Is my code getting faster? Is it getting slower? It can do things like reduce the amount of information that's being passed to our function. In my code, I had an array unique. In my first iteration, right at the beginning, I actually missed that, which means that every point in time after that I was working with that array, it was 10, 100 times bigger than it needed to be, and I was doing things like iterating over it. Think about the data that you need to perform each action, and make sure that you only provide what that function needs. It will save time. XH cloth is pretty heavy. It gets right in there, gets its claws in. I used to say don't use it in production ever, but it can be quite useful. Enable it for 1 in 1,000 requests. Something simple like if empty round 1 in 1,000 equals 42. Enable XH cloth. That way you start to build up some real world usage. Running it on your development machine in a VM is okay. But once you start to run it in production, you start to see how it actually behaves under a production load. That's still only 0.1% of requests. And I've not played with this, but Blackfire has a production mode where you can run it on production code all the time and collect these metrics. So I'm looking forward to checking that out as well. Logging. Use access logs. Observe real-world usage. Work out what code paths are popular. People keep hitting the login page. Let's optimize that. People keep hitting the profile page, the checkout page. People don't really use the search, so why are we spending all of our time trying to optimize it? Take a look at real-world usage to inform what you need to improve. Optimize, cache those common requests. Track everything. Track using available memory on the server. Track response times, timeouts. Track the number of successful and failed requests. When we track execution time for endpoints, we track it by HTTP code. How long does a 200 take? How long does a 500 take? How long does a 400 take? So normally, the 400 takes much less time than the 200 for us, because we do early validation and returns. So by breaking it out by HTTP code, we have a lot more detail, rather than just taking an average of everything. looking at your open socket count, things crash every 3 months. Why? Oh, it turns out that we're not releasing sockets and the server's running out of file descriptors. Unless you're monitoring that kind of thing, you'll probably never find it. And bandwidth usage. If you keep hitting the network, you want to know about that. That's a good indication that there was something there that could be cached. 2 more considerations. The first is, if you are caching, when it expires, is everything going to try and access the data source again? It's what's called stampeding. So what you want to do is have one node that will read something. If it can meet the cache time, say, is this going to expire in the next 10 minutes? Yes, it is. Okay, I'm going to go back to the main, to the master, and say, what is the new data? And I'm going to cache it myself again. So that everything else just continues using the cache and it's never going to expire. You get that stampede effect. And the other one is a circuit breaker. You're talking to an external service, you try it, it fails, you fall back. You try it, it fails, you fall back. That trying and failing is taking time. If that service hasn't worked 10 times in a row, what makes you think it's going to work on the 11th attempt? Using circuit breakers, store your account in memory, memcache, wherever you want. You grab that value, say, check the circuit breaker, is the value over 10? Cool, it's filled 10 times. Let's just go straight to the backup server. Eventually, that will time out in the cache. And then your service will say, check the circuit breaker, it's back to 0. Let's check the original service. And it might be back up by that point. Instead of just hitting it every time, keep track of the state of things. And finally, profiling is all about process. Without process, you're not profiling, you're not refactoring, you're just guessing. Measure, refactor, and measure again. That's the only way you can be sure that the changes that you're making are helping rather than hurting. Is it worth it? I've just spent an hour advocating profiling, but the answer is usually no. No, it's not. In my experience, developer time is more expensive than the CPU time. For most things, I wouldn't even bother. Sticking cache, sure, it takes an hour or so. But unless you have actual real-world constraints, like the example that I gave was a real-world constraint. We worked with a third party, we got 1,000 requests per day, and we had a certain time window to send as much data as we could. That's valid. I'm not just optimizing for the sake of it. There's actual business reasons there. Unless you have a business reason, take the first one, take the array merge, maybe even take the is scalar check, but leave it there. Don't get stuck going deeper and deeper and deeper. I've been Heap. You've been awesome. Thank you for the audience participation.